today's seminar. And then today we have 4 presenters in total. And then let's welcome the first presenter. So you may start with your name.
Okay. Good morning, everyone. Today I will present our lab research on long-term personalized voice monitoring on laryngeal disorders. My presentation is organized into 5 main sections: research, motivation, and objective, system overview, and data introduction, research methods, experiments, and results, and finally conclusion and future works. Let us begin with the research motivation and objectives. This research focused on laryngeal papilloma, a disease characterized by its highly recurrent nature. Patients face extremely high post-surgery relapse risk, and the timing of recurrence is unpredictable. Traditional clinical follow-ups rely on periodic endoscopic examinations, but there is inevitably a time gap between visits during which deterioration may go undetected. This highlights the critical need for a non-invasive long-term voice monitoring mechanism for early detection for relapse signs. On the technology side, deep learning-based pathological voice detection has become a hot research area. However, existing literature mostly focuses on improving the accuracy of general models. The key limitation is that these models overlook inter-individual voice variability. What is abnormal for one person may simply be that person's normal. Therefore, this study proposed a personalized longitudinal monitoring algorithm that established a patient-specific voice health baseline using their own historical data. Okay. The objective of this study is to build an acoustic analysis and anomaly detection system for long-term voice health monitoring targeting laryngeal pneumonia patients. The system analyzed multi-dimensional acoustic parameters, including MXCC, shimmer, jitter, and HNR, using unsupervised learning to track voice changes over time and detect abnormal states. The 3 main contributions are: first, we propose a personalized anomaly detection method applicable to limited sample scenarios. Second, we quantify voice quality changes as objective evidence for treatment evaluation, clinical decision-making. Third, the system enables non-invasive home monitoring that can assist clinicians in early detection of disease deterioration or recovery trends. Next, let me introduce the overall system architect and the data used in this study. This slide shows the overall architecture of our research system. When processing each audio recording, we first extract acoustic features. Then the system simultaneously runs 2 parallel paths. The lower path is the personalized algorithm, comparing the patient's current voice against their own historical recording. This is the core innovation of the study. The other path is the group reference algorithm, comparing against a cohort healthy reference subjects using isolation forwards. After both paths process the same recording, their outputs are combined using adaptive weighting to produce the final presentation, normal or abnormal. All data comes from Far Eastern Memorial Hospital. The recording used the sustained vowel R sound to consist of 22 real patients recording during their clinical visits. The primary purpose of the recording is to assist in clinical diagnosis and disease tracking for recurrent respiratory papillomavirus. In this study, all recordings are indexed as I and J, where is the patient index and J is the recording session index. Now let me explain the research method in details. The The method section covers four major components: feature extraction, personal algorithm, group algorithm, and adaptive gradient. The feature extraction stage is the foundation of our system. Voice signals are pre-processed and then acoustic features are extracted. We extracted two categories of features. First, spectral feature, NFCC, which captures the spectral envelope of the voice. Second, clinical perturbation features, like jitter and shimmer and HNR. After extraction, all features are Z-score normalized. And the MFCC features are dimensionally reduced through PCA. They concentrated horizontally with jitter, shimmer, and HNR to form the final feature vector. Okay. We select three clinically representative indicators. First, jitter, the absolute average difference between adjustment pitch, period length, and represents the total number of pitch period in the sample. A higher jitter value indicates more unstable frequency associated with voice abnormality. And shimmer, the absolute average difference between adjustment period amplitudes. Higher shimmer indicates more unstable amplitude, also associated with voice abnormality. HNR, the ratio of harmonic energy to noise energy. Higher HNR means less noise energy, indicating a more normal voice. Is computed using autocorrelation. Periodic components align when shifted by one pitch period, while noise components do not. So in summary, jitter and shimmer increase with pathological voice. HNR decreases. These three features combined with MFCC provide complementary information for robust anomaly detection. Now, introducing MFCC. MFCC uses a Mel filter bank to simulate the human ear's nonlinear perception of different frequencies, making it well suited for voice analysis. The key idea of MFCC is to simulate human auditory characteristics, filter out unimportant details, extract the most representative vocal tract visual, and compress them into cosine coefficients. The personal algorithm uses DB scan. The core concept is to group points in high density regions into clusters, while points in low density regions are directly classified as noise without forced assignment. The assumption underlying its use here is that a patient's normal voice will cluster into high density regions in feature space, while abnormal voices recordings will appear as low density outliers. Okay, the group algorithm uses isolation forest. It is an unsupervised learning method that does not require labeled data. The key insight is that the anomalies tend to be few and different. The group algorithm is built from 150 healthy subjects to form a healthy norm. It serves as a conservative and stable reference, especially when the patient has insufficient historical data. The figure shows the extracted acoustic feature being fed into the health norm to detect anomalies. These are the parameters we use. The weight between the person algorithm and group algorithm is not fixed. It dynamically changes with the patient's number of recording sessions. Design philosophy is that as the patient's visit count increases, the weight of the personal algorithm increases accordingly. It implements a smooth clinical transition from group comparison to personalized monitoring. The final classification combines both algorithm outputs using the adaptive weights. So if the S is greater or equals to 0.5, the recordings is classified as an anomaly. Now let me present the experimental results and analysis. We evaluate the system using three performance metrics. Sensitivity measures the ability to correctly detect true anomalies. Clinically, we cannot miss a relapse, so high sensitivity is the priority. Specificity, meaning 86, sensitivity 0.86, and specificity is 0.7. The higher sensitivity indicates that the system efficiently detects relapse cases. The longer box plot whisker for specificity indicates that larger individual variability across patients. Finally, let me summarize the conclusion and outline the future research directions. The study proposes an adapted dual-path fusion model for long-term personalized voice monitoring of laryngeal papilloma patients. The three main conclusions are: the dual-path architecture solves data scarcity, and the dynamic weighting mechanism balances early stability with long-term personalization. And three, the high sensitivity of 0.86 demonstrates real clinical potential as a home screening tool. Future directions include incorporation state-of-the-art pre-trained speech models like WaveVect or Huber to improve feature representation and expanding validation across medical hospitals. Thank you for your attention. Any questions?
Okay. We have invited the audience.
Question one. Why did you choose DB scan over other clustering algorithm like K-means for the personal algorithm?
K-means require pre-specifying the number of clusters, which is unsuitable since each patient's voice data has an unknown and potentially irregular distribution shape. DB scan, being density-based, automatically identifies cluster of arbitrary shape and directly labeled low-density points as outliers. Additionally, DB scan does not force every point into a cluster, making it robust to the sparse. So the data typically in clinical genome data sets is used.
The overall sensitivity is 0.7, which means roughly 30% of normal recordings are misclassified as anomalous. How did you plan to address this false anomaly?
The lower specificity mainly stems from two sources. One, the significant individual variability. Some patients have voice characteristics that overlap greatly between their normal and abnormal states, as shown in the LT-AS and spectrogram analysis. And two, the algorithm of group algorithm conservative nature, which flags more anomalies to avoid missing relapse. So clinically, we designed the system to bias toward high sensitivity because missing a relapse is more harmful than a false alarm. So future improvement is through using like what we said, WaveVect or Huber for feature representations.
What was the reasoning behind choosing for as the smoothing constant in the adaptive weighting formula, where W1 equals n over n plus k? Also, how sensitive is the system to changes in this parameter?
The value k equals 4 metric K would reliance on the group norm. So in this study, K equals 4 was applied uniformly across all 22 patients as a fixed hyperparameters. And future work could involve learning of patients' specific K from early visit data to further optimize performance.
Any other questions?
Your system seems to use an unsupervised learning. And may I ask you, how do you handle your own truth label for evaluating performance if there are not
No labels.
no labels trained?
Okay. Well, this is an important distinction. While the training phase of both PD scan and isolation forest is unsupervised, meaning no labels are used to fit the models. The evaluation phase uses clinical ground truth labels provided by physician at the hospital. So each recording session is clinically annotated as normal or abnormal based on the hospital. And these labels are only used as at evaluation. So the design intentionally mimics a real-world deployment scenario where label data is unavailable for building the models. So, but clinician confirmed outcomes can still be used to benchmark system performance.
Okay. Due to the time constraint, so I would like to invite the next presenter, Lin Zhenyi. audience for the questions. Any questions? No question. Okay. Yeah. Would you please? Oh. Okay.
Why design this type of robot? Why? Yeah, why? Because dragging it's not my problem, right? Yeah. But this
Would you please let me get to the slide number 5? So I just realized the motivation behind, why you conduct this research is because of your supervisor.
not only a supervisor.
So can I know who is this guy? Professor Jackie?
Yeah, exactly.
Okay.
I hope until I can ask him the question.
Any questions from you? No? Okay. Would you please navigate to the page 15? Okay, this one, reward function. Yeah, your work, is based on the deep reinforcement learning, right? So I think the beauty part of the reinforcement learning is try to design the reward function properly, right? So may I know the rationale behind with the reward function selection?
You mean behind?
Yeah. Why you choose this process, target, support, balance, distance, and penalty?
Okay, each one. Okay, so first, the progress. You need to encourage your robot mover. So in the beginning, you have to give us little reward to make the robot move up. And the second target is because my robot doesn't have a really precise sensor. It just let me show you the observation. So our observation is the last one. The target is tangible. In real world, I cannot give you a very precise of the distance to the robot. So I divide to 3 levels. One is far and medium and short. And because I only have a camera, don't have the hard. So the target means he wants to reach. He will force him to go there and then try to hook on the pole. And the support is if I don't do that, he like to just one day hold on it because he thinks the agency is the best policy, right? And get the more reward. And the support, the balance is also balance the 3 legs, the support, the weight of each leg. I need to be balanced because I don't want this to hang because it's easier to hold on it. And the distance is encouraged to go to the target, right? And the penalty just adding a lot of the thing. I don't want it to drop off, going down.
Got it. Yeah. Thank you.
Did you have consider to make the little body part to a circle shape that maybe can make it be more easy to balance the robot?
Yes.
So right now your design is square, right?
Yeah.
And is the circle design will be more easy for the robot to be balanced?
I think I can try it, but in a simulate because I want to reduce my training resource and just like a 50 seconds time. So the best way is just use a similar to
Any other questions? Okay, so thank you. I would like to invite the next presenter, Julie. So you may start when you are ready.
In recent years, robotics has developed very rapidly, especially in the area of humanoid robots. Many leading companies such as Boston Dynamics, Tesla, and Unitree are investing heavily in this field. These robots can perform complex tasks such as walking, running, and even jumping. However, despite these impressive capabilities, these systems are still very expensive and highly complex. This motivates us to explore simpler and more accessible approaches to humanoid robotics. Piloting is a very challenging task because this requires coordination of multiple joints, precise force control, and intelligent decision making. Humans must carefully select where to place their hands and feet while maintaining balance. For robots, this becomes even more difficult because they lack natural sensing and intuition. In addition, humanoid robots often have many degrees of freedom, making control and planning extremely complex. To address these challenges, we like to design a simplified humanoid robot with 15 to 18 degrees of freedom. Instead of using a full-scale robot, we focus only on essential joints required for piloting. This reduces complexity while still preserving key functionality. By viewing the system from basic kinetics and matrix operations, I can better understand how motion is generated and controlled. One important reference is the KHR, HP robot. It has 17 degrees of freedom and compact structure. This robot demonstrates that a relatively small system can still perform meaningful humanoid movements. It provides a useful baseline for designing our own robot. For stable fighting, the robot must keep its center of mass close to the wall. This reduces the risk of falling and improves friction between the robot and the surface. Additionally, we use a three-point support strategy. This means that at any time, three links remain in contact with the wall while only one link moves. This significantly improves stability during motion. The robot and the effector is simplified into a hook design instead of multi-finger gripper. This allows the robot to easily hook onto ring-shaped bolts without complex grasping control. By using the hook, the mechanical design and the motion planning robot is whole body, which has only 8 degrees of freedom in each limb. Instead of mechanical gripping, he used magnets to attach the surfaces. This shows the different design approaches can achieve similar planning goals. He also highlights the importance of choosing appropriate mechanism based on the test. Now this is my robot hardware control system design. And this is the servo for the robot. And we have enough torque to do some movement. And it's lightweight and low cost and suitable for real-time event control. We designed a simple circuit board allows the Bluetooth high voltage power to supply all the servos, and also connects to the ground to ensure stable signal transmission. The system wiring is based on PWM control signals. Each servo is connected to power, ground, and the PWM signal line. By adjusting the PWM signal, we can control the angle of each joint. And this simple yet effective setup allows coordinated control of multiple joints. And this our humanoid driving robot side. It has a total of 17 active joints, including arms, legs, and the torso. The robot is compact and lightweight, making it easier to test and modify. And also has 2 testing joints. Instead, install two hands globally. You will rotate with the screen according to the service to change the angle that make the robot can catch the whole more stable. Despite its small size, it retains the key humanoid features necessary for pilot. And this the basic joint. It rotates not by servo. And this is the joint table. The table summarizes the joint range and degrees of freedom. Each joint has a defined range to prevent mechanical damage and ensure safe operation. Understanding these limits is important when designing motion trajectories. They also help avoid unrealistic or unsafe movements due to the servo placement and the rotation. The joint rotation angle has positive and the negative direction. This is the simulation setup. We use Ninja Code as a simulation body. As you can see in the picture, it has a wall and 8 holes. The red holes is the standby holes for the robot to catch. And in my system, I mainly use 4 kinematics to control motion. This means calculating the position of an effector based on the joint angle. The robot's motion is defined by kinetic chains. And my robot each arm have 3 servos. One is shoulder, and one is elbow, and one is wrist. The impactor is the best joint, so we didn't rotate by the servo. And my neck have 5 servos. Hip low, hip below, and the hip pitch near to angle. And then the back is the book. This is a transformation metric. To compute the n factor position, we use transformation matrices. Each join contributes a transformation and by multiplying then together we get the final box. This method is fundamental in robotics and provides a precise mathematical model. This slide shows predefined power motion stages. The start pose is there are three figures. Well, this is shoulder, and this elbow, and this is wrist. So this is the angle. So the start pose is each figure is 0. Then the robot will press its up, then approach to the pose, and then hook catch. Hook means catch the hook. This is for the leg motion control. Real testing, PRLearning, is mean fast speed modulation. Is the fundamental method used to communicate with the robot servos. It works by sending a series of digital pulse pulses. Where the width or duration of the pulse tells the servo which is at angular position to hold. And at project, the PRL signal is carefully limited to safe benches. And this lies nation in control. As you can see in the video, my robot is left arm to catch the hole. Then is the right arm to catch the hole. Then is the back leg. This is the schema pose. If it can complete movement or pose, then it can keep climbing to catch the blue pose. And this is a simple testing for blue. Every time start from the right arm and left arm. You may think move slowly, but it's just a simple test. Then move its right leg. Okay. In future work, I tend to scan this project in 3 directions. First, for advanced perception and interaction intent. I aim to integrate both vision and both sensing. For vision, I plan to use depth sensors to generate accurate depth maps. These maps will help the robot detect the position and the shapes of guiding hooks more reliably. And second, for hierarchical planning, I will combine global strategy with local control. And finally, for reinforcement learning and sensorial transfer, I plan to enhance the robot's adaptability by shaping the action space. The robot can learn more efficient and stable behaviors. I will also use domain visualization, conservation environments, where this more stable real-time control, and a more precise low-level hardware access through GPIO and the PWM compared to ESP32.
Any questions? Okay. I have one question for you. On your presentation, I just realized you provide quite comprehensive introduction regarding the robust spec and the simulation process, right? But I don't know what kind of research problems you got, or what kind of research field you are closing out.
Yeah,
Because for the master student, you have to publish paper, right? And then you have to find some research problems there and try to solve it or try to achieve it. But for this presentation, you can use some there.
yeah, because I spent a lot of time to design the robot, so in my future work, I will use reinforcement learning to train, do some work.
So you still have one more year to go.
Yeah, my professor.
Okay.
Okay. Want me to give
Okay.
all the
Okay.
process?
Sorry to hear that.
Okay.
Okay. Thank you. Good luck. Okay, let's invite the next presenter, Du Mingji.
Good morning, everyone. My name is Ingrid. Today I will present an AI-assisted web-based educational support system for Android universities. Here is the outline of my presentation. I will start with the introduction to the tool, and I will explain our contribution to the system. Present a experimental result and end with the conclusion and the application. In my mentioned education, Android support play a very important role because they help students in motivation or work. We propose the word-based system. This recognizes the angel and find returns to technology and allows small signal quality simulation using physics. The page form shows them clear forms and formulate here, so students can verify ideas immediately.
technical problems. So I'd like to open the floor for questions. Any questions?